Hi, I'm Brian Gaines, a machine learning developer in the analytics division of R&D at SAS. In this video, I discuss one of my favorite machine learning models, the Generalized Additive Model, or GAM for short. In addition to providing you with an overview of GAMs and their attractive features, I also show you how easy it is to use Model Studio to train a GAM and compare it with other models. As you will see, GAMs are appealing because they strike a nice balance between flexibility and performance while maintaining a high degree of interpretability. Before we look at GAMs, let's first briefly review a common statistical model that you are likely to be familiar with, the Generalized Linear Model, or GLM. A GLM is a very popular and flexible extension of the classical linear regression model because it enables you to model a target or response variable that is not normally distributed. For example, if your goal is to predict whether an incoming email is spam, or you want to predict the number of people shopping at a grocery store, the linear regression model is inappropriate because the target variables for those applications violate the model's normality assumption. However, a GLM can handle both data types by assuming an appropriate distribution and by using a link function to relate the linear predictor to the distribution mean. A GAM extends a GLM even further by relaxing the linearity assumption. For GAMs, the component functions can be arbitrary nonlinear smoothing functions that the model usually estimates by using splines. Therefore, not only can GAMs model different types of data just like GLMs can, but GAMs also take this flexibility to another level by incorporating nonlinear functions that can model more complex relationships. Even with this flexibility, GAMs are still interpretable. This is an increasingly desirable feature of machine learning models, especially for high-stakes applications such as healthcare, finance, and mission-critical systems. Typically, you face a trade-off between model performance and model interpretability. At one end of this spectrum, you have transparent models such as the ordinary linear regression model. Although it is often outperformed by other models, one of the reasons for its sustained popularity is because it is easy to understand. At the other end of this spectrum, you have opaque machine learning models such as neural networks, gradient boosting machines, random forest, and support vector machines. These state-of-the-art models can predict very complex relationships extremely well, but it is difficult to interpret how the inputs affect the predictions. A highly accurate model might not be put into practice if domain experts and other stakeholders do not understand it. GAMs occupy a sweet spot along the performance and interpretability spectrum. With their ability to model complex relationships, GAMs have predictive performance that is usually competitive with other machine learning techniques. When it comes to interpretability, the additivity of the component functions enables you to decouple the effects from the different terms. So you can plot an estimated component function for an individual input to visually interpret that input's contribution to the prediction, which you will see later. Now that you have a better understanding of GAMs and their benefits, let's see a GAM in action. The GAM node in Model Studio, part of SAS Visual Data Mining and Machine Learning in SAS Viya, provides a user interface to the GAM select and GAM mod procedures that lets you train a GAM without writing any code. To do that, let's revisit an example from the literature that trains a GAM to predict the probability that a mortgage applicant will default on a loan. To reproduce this example, refer to the companion SAS Communities article for the code to create and process the dataset. For this, let's open SAS Studio. After you run the code to load the data table in SAS Studio, open the Applications menu in the upper left corner and select Build Models to switch to Model Studio. Within Model Studio, select New Project and give the project the name Mortgage Default. Next, for the data, select the HMEQ-LC dataset. Click Save to create the project. On the Data tab, select the bad variable and assign it to the role of target. Next, select the part variable, assign it to a role of partition, select Map Partition Levels, and map training level to 0 and test level to 1. Now switch to the Pipelines tab to create a model building pipeline. To add a GAM node to your pipeline, right-click the data node, then click Add Child Node, Supervised Learning, and finally GAM. The GAM node enables you to train a GAM without having to write any code. As you can see, the node contains a variety of options to customize your analysis, such as the interval target probability distribution, the target length function, effects options, and options related to the chosen selection method. For example, let's use the UI to train a model similar to the one in the Lam and Kai paper. First, expand the effects options group, and then click the button next to the bivariate splines group to add bivariate splines to the model. Next, select Use All Observations to construct spline basis functions. Now, let's expand the boosting options group and set the learning rate to 0.2. Final two changes are to set early stopping stagnation to 10 and early stopping tolerance to 0.0005. Click the play button at the top of the node to run the node. When the model training is complete, right-click the GAM node and select Results to view the model's results. For the effects in the final model, the results include smoothing component plots for the spline terms and parameter estimates for the parametric terms. For example, the results include a smoothing component plot for the spline term for the debt-to-income ratio input variable. As you might expect, the probability of default is generally higher for an applicant who has a high debt-to-income ratio. Now that you have used the GAM node to train a GAM, let's train a few other models for comparison, which you can easily do in Model Studio. Repeat the previous steps to add a supervised learning node to your pipeline to add the gradient boosting, logistic regression, neural network, and SVM nodes. Click Run Pipeline to train and compare all these models. Right-click the Model Comparison node to view the results. If you sort the algorithms by misclassification rate, you see that the GAM ranks second. Even though the GAM has a slightly higher misclassification rate, it is more interpretable than the Champion gradient boosting model and still outperforms other complex models such as SVM and neural network. As you can see, Model Studio enables you to easily train a GAM alongside other machine learning models and to compare model performance. This is done in just a few clicks and keystrokes to make analytics accessible to everyone and to empower you to use data more easily to answer questions. GAMs are enticing because they provide a solution to the dilemma of choosing between accuracy and interpretability. So it's easy to see why GAMs belong in every data scientist's toolbox. For more information, please visit the SAS Visual Data Mining and Machine Learning product page and the Model Studio User's Guide. Thanks for watching.